గుడ్ మార్నింగ్ ఎవ్రీబడి. ఈరోజు ప్రపంచం మొత్తం మీద కోవిడ్-19 విస్తరిస్తోంది. ఈ కరోనా వైరస్ విపరీతంగా కరాల నృత్యం చేస్తుంది. కాబట్టి ప్రతి ఒక్కరూ బయటకు వెళ్ళేటప్పుడు ఖచ్చితంగా మాస్క్ లేకుండా వెళ్ళొద్దు. మాస్క్ వేసుకునే వెళ్ళండి. ఇంటిలోకి వచ్చిన తర్వాత మాస్క్ తీయండి. అంతవరకు మాస్క్ వేసుకోండి. థ్యాంక్ యూ. టుడే we are discussing about real numbers continuous chapter. In the previous class we are discussing about the number system. In the number system, set of natural numbers n is equal to 1, 2, 3, 4 and so on. Set of whole numbers or w is equal to 0, 1, 2, 3, 4, 5 and so on. Set of integers z is equal to set of and so on, -4, -3, -2, -1, 0, 1, 2, 3, 4 and so on. And set of quotient numbers or rational numbers, or q is equal to set of p by q. Here p, q are integers and q not equals to 0. And the irrational numbers. Irrational numbers are nothing but those numbers are not rational numbers are known as irrational numbers. Irrational numbers examples: s is equal to or q dash is equal to √2, square root of 3, square root of 5, square root of 6, square root of 7, square root of 8, square root of 10, square root of 11 and so on. Means those numbers are not perfect squares, are known as irrational numbers. So what are the main operations in the real numbers? In the real numbers, main operation is division algorithm. Euclid states this division algorithm in his book Elements. So before division algorithm, we are discussing normal divisions. You know very well, 12 divided by 5, a simple division. 5 2s are 10, remainder is 2. This is quotient. This is remainder. Normal division rule is dividendo equals to divisor into quotient divisor into quotient plus remainder. This is division rule. Means here 12 equals to divisor 5 into quotient 2 plus remainder 2. 5 2s are 10 plus 2 equals to 12. Verify. This is division rule. We very well known this is. This is nothing but according to Euclid's division algorithm, for some integer a equals to, for any integer a equals to bq plus r. Here b, here essential condition is 0 less than or equal to R less than B. Q is quotient, you know very well. R is remainder, B is a factor. Means nothing but divisor. So A is equal to for any integer, A is equal to BQ plus R. This is Euclid's division algorithm. How we can define the Euclid's division algorithm? Euclid's division algorithm states that given positive integer A and B, there exist unique pairs of integers Q and R satisfying A is equal to BQ plus R. Here 0 less than or equal to R less than B. So definition in words. Euclid's division algorithm. Euclid's division algorithm. Or Euclid's division lemma. Given positive integers, A and B, there exist unique pair of Q and R, unique pair of integers Q and R satisfying A is equal to BQ plus R. Here 0 less than or equal to R less than B. The remainder should be lies between 0 and B including 0. That is the essential condition here. This is Euclid's division algorithm. Given positive integers A and B, there exists a unique pair of integers Q and R satisfying A is equal to BQ plus R. Here 0 less than or equal to R less than B. This is Euclid's division lemma. By this using, we have to find the HCF of any two numbers. This is illustrated examples for 60 and 100. How can you find the HCF? 60 and 100, big number is 100, is equal to, for the 60 into 1 plus 40. This is remainder. Again, this remainder equals to, this 60 equals to, from this remainder 40 into 1 plus 20. This 40 equals to, this 20 into 2 is plus 0. We get 0 here. In this case, we got 0 remainder. That's why 20 is the HCF of 60 and 100. In this case, we got 0 as remainder. That's why 20 is HCF of. In this case, remainder is 0. Therefore, the HCF of for 60 and 100 is 20. HCF means highest common factor. Is nothing but GCD, greatest common divisor. HCF of 160 is 20. This is the final answer. Now, you can do the homework. Do this in the page number 4. From textbook. This is homework for you. Another small theoretical example is there in our textbook. Now we are discussing about it. Given that a group of bees settled on some flowers according to given, if two equal not two equal number of if equal number of bees settled on two flowers, if equal number of bees settled on two flowers, then one bee will be left. One bee will be left. For example, the number of total bees will be X. Then two equal number of bees. Now, the equal number of bees settled on two flowers. Two flowers మీద ఈక్వల్ నంబర్స్ కలిగినటువంటి బీస్ గ్రూప్ సెటిల్ అయితే వన్ బీ విల్ బి లెఫ్ట్. మీన్స్ టూ పార్ట్స్గా డివైడ్ చేస్తే బీస్ని టూ పార్ట్స్గా డివైడ్ చేస్తే వన్ బీ remaining. So remainder is 1 here. And other condition, if the bees settled on 3 flowers in equal number then 2 will be left. Means the number of bees, total number of bees x is equal to 3 parts का divide చేస్తే means b 3 into b plus 2 remainder is 2 3 parts to b in each part containing the number of bees. Another condition is given there. If the bees settle on 4 flowers in equal number then 3 will be left. Means x is equal to 4c plus 3. Last condition is if the bees settled on 5 flowers in equal number no bees will be left. Means 5 equal parts గా డివైడ్ చేస్తే number of bees ని bees no left means remainder is 0 here. So 5x the total number of bees x is equal to 5 into d plus 0. This is the very important clue for us to find the number of total bees in this example. Why? There is no remainder when we have to divide in 5 groups the total bees. That's why the multiples of 5 will be came to the answer. Means according to this equation the number of total bees may be 5, 10, 15, 20, 25, 30, 35, 40 and so on. According to this equation, the total number of bees may be 5, 10, 15, 20, 25, 30, 35, 40 and so on. Means multiples of 5. So now going to this condition, x is equal to 4c plus 3 means the total number of bees will be dividing into 4 groups. 3 bees will be left. Then 4 3s are 12. Maybe here according to x is equal to 4c plus 3, the possible answers are the possible number of total bees will be 15. Next 35. These are all 15 and 35. Because 4 3s are 12. 3 groups का डिवाइड होते हैं 12 होते हैं 3 20 लेफ्ट आउट है तो सही होता है. అలాగే 4 8s are 32. and also there also 3 will be left. Means 5, 15 or 35 are the possible answers. Now the before condition is when they are settled on 3 flowers పైన సెటిల్ అయితే ఎట్లా వస్తుంది x is equal to for 3 flowers x is equal to 3b plus 2 will be left. It's not. It's very impossible because of 3 5s are 15, no b's. 3 11s are 33, 2 will be left. Satisfies this equation. That's why 35. 35 will be answer. Possible answer is possible number is 35. For 2, the first condition, if the bees will be settled on 2 flowers, for 2 flowers, x is equal to 2a plus 1. 2 17s are 34, remaining is 1. This is also satisfies. So possible answer is possible number is equal to 30. So finally the number of total bees will be 35. Therefore the number of total bees 35. All conditions will be satisfied for 35. If 2 groups dividing there, if the bees will be settled on 2 flowers in equal numbers, then 2 17s and one bee will be left. And if the bees will be settled on 3 flowers, then 2 will be left. 3 11s 33, 35 minus 33, 2 bees. Next, if they are settled on 4 flowers in equal numbers, 4 8s are 32, 3 will be left. If they are settled 5 flowers in equal numbers, 5 7s are 35, no remainder, no bees will be left. That's why the final answer is the number of total bees is 35. This is also that according to these given conditions, if we have to examine there, x is equal to 2a plus 1, x is equal to 3b plus 2, x is equal to 4c plus 3, x is equal to 5d plus 0. These are all refers the division rule. These are all. We have to examine there. These are 2, 3, 4, 5 devices. A, B, C, D. Some quotients. 1, 2, 3, 0. Here remainders. So this is division algorithm. That's why Euclid's division algorithm very useful to find any solution for some solutions. Now we are going to discussing about some examples, textbook examples. These are refers division algorithm. Simply we can say division rule. Now textbook examples. First example is in our textbook. First example is before examples we are finding HCF of in this do in your textbook do these examples find HCF of 1860 and 2015. Given numbers '60 and 2015. The big number is 2015 is equal to 1860 into 1 plus 155. 2015 1860 155 is the remainder. Again 1860 is equal to 155 into 155 into 12. 12 5s are 60, 12 5s are 60, 66. 12 1s are 12 plus 2, 18. So 12 plus 0. In this case, we got the 0 as the remainder. That's why 155 is the HCF for these two numbers. Therefore, HCF is the highest common factor. Highest common factor is nothing but greatest common divisor. GCD or HCF. HCF of 1860 and 2015 is 155. Textbook examples. The first example in the page number 5. Actual examples. Example 1. Question is positive even integer is of the form 2q and that every positive odd integer is of the form 2q plus 1. Show that every positive integer is of the form 2q and that every positive odd integer is of the form 2 is of the form 2q plus 1. Q is some integer. Q is some integer. This is the question. Now solution. Let us consider some a is a positive integer. Positive integer. And b is equal to, then according to Euclid's algorithm, according to Euclid's division lemma, A is equal to BQ plus or 0, sorry, or 0 less than or equal to R less than B. This implies A is some positive integer, A is equal to BQ plus R. BQ means B is equal to here because of the given numbers should be in the form of 2q, odd numbers will be in the form of 2q plus 1 are the required proofs. That's why B is equal to, take 2q plus R. 2q plus R. A is equal to 2q plus R. Here condition is 0 less than or equal to R less than 2 because B is equal to 2. So R lies between 0 and 2 including 0. That's why therefore the remainder may be R is equal 0, 1 since R less than or equal to 2. If R equals to 0, then A is equal to 2q plus 0. Therefore, A is equal to 2q. This is even integer. When integer formula 2p or 2x or 2q or 2x. Therefore, this is given number. If R is equal to 1, then A is equal to 2q plus 1. It is odd number, odd integer. Therefore, every positive even integer is of form 2q and every positive odd integer is of the form 2q plus 1. This is the proof according to Euclid's algorithm. Euclid's division algorithm or Euclid's division lemma. The second example is also there. Second example
show that any positive odd integer is of the form 4q plus 1 or 4q plus 3, where q is some integer. This is the question. In the same page number 5, textbook. Yes.
So the second question, second example is show that any positive odd integer is of the form is of the form 4q plus 1 or 4q plus 3. Here q is some integer. Q is some integer. The solution. How we solve it? According to Euclid's division lemma. If A is any positive integer, if A is any positive integer, then A is any positive odd integer, then and we have to take in B is equal to 4, then according to Euclid's division algorithm, A is equal to BQ plus R. Here 0 less than or equal to R less than B. This implies for this condition A is equal, B is equal to 4 is here, 4q plus R, 0 less than R less than 4. What are the remainders? Possible remainders here. The remainders lies between 0 and 4 including 0. Therefore, remainders may be R equals to, because 0 less than or equal to or less than 4 implies R is equal to 0, 1, 2, 3. Zero including, but less than 4 only, not including 4. 0 including here, not including 4. Less than 4 means up to 3. Then we got the remainders here. R is equal to, remainder R is equal to 0, 1, 2, 3 only. If R equals to 0, if R equals to 0, then A is equal to 4q plus 0. Therefore, A is equal to 4q. This is even integer. Why? Because 4q. Again, it is in the form of 2 into 2q is equal to 2p. It is even. Here P is equal to 2p belongs to Z. Q belongs to Z. It is even integer. So it's known. Next, if R is equals to, next value is 1. If R is equal to 1, then A is equal to 4q plus 1. It is clear. All integer. If r is equal to 2, then A is equal to 4q plus 2. It is again 2 if we have to take a common, 2q plus 1. Again it is in the form of 2x. So even. If r is equal to last value, r equals to 3. If r is equal to 3, then A is equal to 4q plus 3 is equal to 4q plus 2 plus 1. 2 common in these two terms, 2q plus 1 plus 1. Again it is in the form of 2x plus 1 or 2y plus 1 odd number. In this example, we can observe that A is equal to 4q plus 1 here. So 4q plus 3 is odd because of it is in the form of 2y plus 1. That's why 4q plus 3 is also odd. A is equal to 4q plus 1 and A is equal to 4q plus 3 odd numbers, odd integers. Therefore, every positive odd integer, every positive odd integer is of the form 4q plus 1 or 4q plus 3. These two examples are over. Now, exercise 1.1 in the page number 5. Do the homework. If you have to trouble in the exercise, I will explain in the next class. Now we have to discussing about the fundamental theorem of arithmetic. Fundamental theorem of arithmetic. Every composite number can be expressed as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. This is the fundamental theorem of arithmetic. Yes, is it clear? Now I can erase. Fundamental theorem of arithmetic. Fundamental theorem of arithmetic. This theorem states that every composite number can be expressed in the form of the product of prime numbers in this unique way. This is in unique way. The statement is every composite number can be expressed expression means factorized, can be expressed as a product of primes.